In Cameroon, if you want to get into medical school, you need to be successful at the medical school entrance exam. It's a competitive exam, and you're going to be tested on A-level concepts in physics, chemistry, biology, general knowledge, and French or English. And in this video, we will look at a few questions in the physics section of the 2023 edition of this exam. The first question, so this was question 83 on the original paper. A ball is rolled on the edge of a horizontal table with speed 4 meters per second. It hits the ground 0.4 seconds later. Which of the following statements is correct? Let us draw the floor. Here is the table, and here is the ball at the edge of the table. They say the ball is rolled with a speed 4 meters per second. We are going to ignore air resistance and assume that this 4 meters per second is just in the x direction. So we have no vertical component of speed. Now, because of gravity, we expect this ball to follow a projectile path, something like this. Now, the point at which this path intersects the floor will help us to determine the angle of impact. The whole of this journey is going to take 0.4 seconds. So let's look at the options. So A, it hits the ground at a 90-degree angle. Let's look at it. So it hits the ground at a certain angle. So this is the angle the tangent that we talked about makes with the horizontal line or the x-axis. And this angle is clearly not 90. So A is wrong. B, the height of the table is 9.8 meters. So let's try to find the height of the table. So here is the height of the table, h. So h corresponds to the magnitude of the vertical displacement of the ball. Given that there is no vertical component of speed, we can just apply the formula that we all know since secondary school. H equals to half gt squared, and we know that g is the gravitational field strength, and then t is the time. So let's go, h is equals to half, g could be 9.8 when nothing is given, we just assume it's 9.8, and then t is 0.4, and we square that. Now for this to give you 9.8, 0.4 squared has to give you 2. So 0.4 squared is clearly not 2. That is why B is not correct. C, the ball touches the ground at a horizontal distance of 1.6 meters from the edge of the table. Horizontal displacement. So the horizontal displacement is this distance here, from here to here. So the horizontal displacement of the ball is going to be given by, let's call it d. Since we have no acceleration in the x-axis, we only have a speed that we assume is going to be constant. Distance is speed times time. Everyone knows that. So we have the speed in the x direction times the time for the whole journey. So we have 4 meters per second times the time, which is 0.4 seconds. So when you compute this, you have 1.6 meter. So C is correct. So at this point, we could just move on to the next question. Well, D, the ball follows a linear trajectory before hitting the ground. That is clearly wrong because of the X component of speed. So that's it. Let's look at the next question. Which of the following is the reason why an equilibrium point may not be found in a potentiometer experiment? All right. Before we look at the potentiometer, let us just look at what they are referring to when they talk about the equilibrium point. So suppose you find a cell in your house. You don't know the potential difference across this cell. And then, you find out you actually have 2 of them. And you connect them this way. So this type of connection of 2 cells is called a parallel connection. Because you have connected the positive terminals of the cells together and the negative terminals together. Now, if these 2 cells are identical, and I ask you the value of the current that is flowing in the circuit, did you say 0? So the current through the galvanometer, yes, is going to be 0 ampere. Why is it so? It's simply because the potential at this point is the same as the potential here. And so there is no reason for current to flow from a region of a certain potential to another one of the same potential, since the potential difference is going to be zero. Through the potentiometer experiment, you will want to achieve a situation in which the galvanometer reading is going to be 0 ampere. Now let's look at the potentiometer itself. So a potentiometer is something like this. You have a galvanometer, and then here you have a sliding contact. So the sliding contact is sliding along a resistance wire, so something like that, which in turn is connected to the terminals of a driver cell. So the driver cell is connected in such a way that the positive terminal of the driver cell is in contact with the positive terminal of the test cell. Now, what is happening in a potentiometer experiment? So the extremities of this resistance wire are X on the positive side and then Y on the negative side. And then we have the point at which this lower loop is coming in contact with the resistance wire. We call it C. So initially C is closer to X, and then we are progressively sliding the point of contact C towards Y and observing the reading on the galvanometer. So when C is leaving from this left side towards the right, what is happening is that the potential difference between X and the point of contact C is going to increase because the length from X to C is increasing. We know that generally on a resistance wire, the resistance represented by a certain length is the length times the resistance per unit length, so that we have the resistance at that length. So the longer the distance from X to C, the higher the potential difference that is building up. And eventually, as we are sliding C along XY towards Y, we will come to a point of C. So C is going to be at a position where the potential difference between X and C will be very similar to what we initially saw. And the galvanometer reading is going to be 0. And that is the equilibrium position. So the potentiometer experiment is all about using different test cells and determining the length at which each test cell is going to achieve equilibrium. So if we have the first length, we can liken it to the first EMF if we're talking about test cells, because since there is no current in the galvanometer, there is no internal resistance in the cell. So what you're going to be measuring at equilibrium is actually the EMF. And then you will have a second length, L2, and then you will have a second EMF. And this is the relationship between these four quantities. So it means that if I bring another cell and I know the potential difference of the cell or the EMF of that cell, and then I have a certain length I can measure on the potentiometer, and then we have this first length of equilibrium with our test cell, and we don't know this, we multiply both sides by E2, and then we are going to have the value of the electromotive force in the test cell. So that is one way of using the potentiometer. Now that we have seen what the potentiometer is all about, let's go back to our question. Which of the following is the reason why an equilibrium point may not be found in a potentiometer experiment? A. The positive terminal of the test cell connected to the positive terminal of the driver cell. So you are obliged to have such a setup to have equilibrium. So the answer is not A. So that's actually what you should do to observe an equilibrium point. Otherwise, you'll be connecting the batteries in series, and that's not what we're trying to do. B. The potential difference of the pilot cell is greater than the potential difference at the edge of the potentiometer wire. Now, here the problem is the English. So I just want to believe that this was intended, because you can't have the potential difference at a point. So when they say the potential difference of the pilot cell, okay, I think they mean the potential difference across the pilot cell is greater than the potential difference at the edge. How can we talk about the potential difference at an edge? They could say across the edges, but at a single edge doesn't really make sense in English or in, I don't know, physics. C, the potential difference to be measured is greater than the potential difference across the potentiometer wire. So that sounds plausible. So imagine that we are sliding this C along XY. So we are expecting the potential difference between X and the point C to progressively increase as C is getting closer to Y. But if the test cell has a bigger potential difference, we would reach Y and we would still not have found a point at which equilibrium is achieved. So yes, if the test cell has a higher PD than the driver cell, there is no way we will achieve equilibrium in a potentiometer. So C is correct. D, the potentiometer wire is not uniform and long enough. Now, the uniformity of the potentiometer or the length of the potentiometer are factors that will affect the accuracy of the experiment, because an assumption that we are making when we have this relationship is that each unit length, whether it's centimeter or millimeter, of this wire represents the same resistance. So the assumption is that the resistance per unit length is identical all through the resistance wire. And strictly speaking, this will never be true. There are always imperfections. So there is always a margin of error. But if the margin of error is big, it doesn't mean we won't have the equilibrium position. It's just that the calculations are not going to be very accurate. So the answer is C. Let's move on to the next question. A capillary tube of diameter 2 millimeters is held vertically in clean water of density 1000 kg per meter cubed. The surface tension of water is 7.2 times 10 to the negative 2 Newton per meter. How high will the water rise in the tube? All right, so let's sketch what's happening in this question. So we have some water and then we insert a capillary tube. So when we insert a capillary tube, we shall observe a capillary rise, and they are asking us to find the height at which the water is going to settle in the capillary tube. Certainly the height from the level at which you would expect the water to be if there were no capillary action. The reason why we have a rise when there is a glass capillary tube inserted in water, is because adhesive forces between the water and the glass are greater than cohesive forces. So how high it goes depends on how strong the surface tension forces are, but whether it rises or not depends on whether adhesive forces are greater than cohesive forces. Now, what happens here? At equilibrium, we know all the forces are balanced, and there are two forces here. The first force is the weight of the water. So we have the weight W, and the weight has to balance the upward force. If we have to zoom this interface, let's try to zoom this interface here. So we have something like this. And we are going to have an angle of contact. So the angle of contact is simply the tangent generated by the point of contact between the surface molecules of water and the glass. So we have the surface tension forces acting in this direction, the direction of the angle of contact. And then we want to find out what is the vertical component of these surface tension forces. So we know that the vertical component in this case is going to be given by F cos theta. And this force has to be balanced by the weight. So the equation is the weight, which is mass, the mass of the water that has risen, times gravity. So the weight has to be equals to the vertical component of surface tension. So we have mass times gravity has to be equal to the force caused by surface tension times cos theta. So the mass of the water that has risen is the density times the volume, and then times gravity, we have the weight. And then F, which is surface tension force, is going to be given by gamma, the surface tension, which is the force per unit length. The length here is going to be the circumference. Let's call it L times cos theta. So let's further simplify this. We have rho. Instead of volume, we put cross-sectional area times the height. So we have pi radius square times height times gravitational field strength will be equal to gamma for surface tension force per unit length times the length, which is going to be 2 pi radius times cos theta. So we are looking for, so what are we looking for? We are looking for height. So this is what we are looking for. So we will make that the subject of the formula. We have h equals gamma 2 pi radius cos theta divided by rho pi radius square times gravitational pull. Pi will cancel, this radius will take this square, and then we will be left with h equals gamma, so 2 gamma cos theta divided by rho rg. So this formula tells us that all things being equal, the higher the radius, the smaller the height. So if the radius of the capillary tube is very large, the height is not going to be noticeable. And if the radius of the capillary tube is very small, the height is going to be noticeable because it's going to be high. All right, let's compute that. Water and glass are usually in love with each other. So we expect a very small angle of contact. So a small angle of contact is going to imply cos theta being close to 1. So we can assume cos theta is 1. So the height is going to be equals to 2 gamma divided by rho rg. So let's compute that. So 2 gamma is given by 7.2 times 10 to the negative 2. Rho is 1000. The radius is 10 to the negative 3 meters. And then we have g, which is 9.8. So when we compute that, we have 14.7 millimeters. So that is the height. A moving coil galvanometer with a resistance of 300 ohms gives a full-scale deflection of 1 milliampere. The shunt resistance R needed to convert the galvanometer to an ammeter of 3 amperes is? So we have a galvanometer like this, and the full-scale deflection of the galvanometer is 1 milliampere. So the current that has the maximum current that should flow on this galvanometer is 1 milliampere, and the resistance of the galvanometer is 300 ohms. We want it to be able to measure current of 3 amperes. So for that to be possible, we need to connect a shunt in parallel with the galvanometer in such a way that the shunt is going to pick up 2.999 amperes and allow just 1 milliampere, which is 0.001 ampere, to flow into the galvanometer. So this is actually the problem, and they are asking us to determine the resistance of the shunt. So it's pretty straightforward. We know the current, we know the potential difference, because the potential difference between A and B is the same across the galvanometer and across the resistor. So all you need to do is, you know that the potential difference is the current times the resistance, and if you're looking for the resistance, you just have to apply this and you have your answer. So V is going to be given by 300 times 0.001, and then the I here is the I that is flowing through the resistor, which is going to be 2.999. So all you need to do is compute that. So we have 0.100 ohm. So the answer is C. A moving coil galvanometer of resistance 20 ohms gives a full-scale deflection for a current of 2 milliamperes with an external resistance of 200 ohms. The coil galvanometer can be used as a... Alright, so let's have a sketch for the question. So the full-scale deflection of the galvanometer is 2 milliamperes, and the resistance of the galvanometer is 20 ohms. And this is connected to an external resistance R of 200 ohms. There are two questions actually. So what is the use of such a setup? So this setup is used to convert a galvanometer into a voltmeter, and this resistor here is called a multiplier. Now, what the question is asking us to do is to determine the maximum potential difference from A to B. So you just have to sum. So the potential difference VAB is equal to the potential difference across the galvanometer plus the potential difference across the resistor. So let's go. V galvanometer is just I galvanometer at full scale deflection times the resistance of the galvanometer, and then you just add the resistor of the multiplier multiplied by the same current at full scale deflection. So this is going to give us I of galvanometer plus I into I of the galvanometer into resistance of the galvanometer plus resistance of the resistor. So numerically that is going to be, so this will give us 0.44 volts. And this corresponds to none of the answers that were proposed. Alright, we have come to the end of this video. I hope you enjoyed it. If it's the case, then please don't forget to click the like button and to share this video. And if you want us to treat any questions, just put them in the chat below. You can just post a picture of the question if there are diagrams or formulas, or you could just copy and paste the question in the chat box. That being said, looking forward to having you watch our next video. Bye-bye.